Hello everyone, and welcome back to some more remote learning. In today's video, we're going to do some examples on the mean value theorem and then eventually on Rolle's theorem. So let's get ready to roll. For mean value theorem, as long as certain conditions are met, then there is some point or points within the stated interval where that slope of the tangent line at that point, so the derivative at that point, is equal to the slope of the secant line formed by the endpoints of the interval. And the conditions that I'm talking about are that we have some closed interval from some point A to some point B. That interval has to be closed in order to use the mean value theorem, and our function also has to be differentiable within that interval. If those conditions are met, we have a closed interval and our function is differentiable, then we can say that slope of the secant line formed by those endpoints, how would we write that? Do you remember how to write the slope of the secant line? Change in y over change in x. So that slope is going to be f of b, the y value at our point B, minus f of a, the y value or function value at our point A, all over our x value at our point B minus our x value at our point A. So that's going to be b minus a. That is the slope of the secant. And what the mean value theorem says is that the slope of the secant is going to be equal to f prime of c, the derivative at some point c. So again, one more time, the mean value theorem says that. So if I drew that secant line in blue from A to B, then I'm going to have a parallel because I'm going to have the same slope. So I'm going to have a parallel tangent line somewhere else within that interval, and you can see that occurs at point C. So the slope of the secant line is equal to the slope of the tangent line at some point within that interval. So in example 1, for each of the following, we're going to find the point or points C for the mean value theorem of our given function and the given interval. So we have to check two things first before we even start these problems. Do we have a closed interval, and are we differentiable everywhere within that interval? So looking at part A, zooming on in, we know that we're differentiable for this polynomial x squared minus 5x everywhere along that. For any x value, we're differentiable. And we do indeed have some closed interval from 1 to 5. So because those conditions are met, then we can go ahead and use the mean value theorem to find some point C where that derivative is equal to the slope of the secant line formed by x equals 1 and x equals 5. So again, f of b minus f of a all over b minus a is going to equal the derivative at some point C. So what we're going to do is we're going to fill in the given information and attempt to find C. So I'm going to have b, b5, and then my point A is going to be an x value of 1. So I'm going to have f of 5 minus f of 1 all over 5 minus 1. That's going to be equal to f prime of c. C is what I'm solving for. So f of 5, if I was to plug 5 in for x, I would get 5 squared minus 5 times 5. 5 squared is 25, minus 5 times 5 is 25. So when I'm at x of 5, I'm at a y value of 0. So this point is 5, 0. So f of 5 is 0. I'll go ahead and fill that in. And then I'm subtracting. When I plug 1 in, I'll get 1 squared minus 5 times 1. That's 1 minus 5, which is going to give me a negative 4. So this point is 1, negative 4. So f of a, f of 1, is a negative 4. So now if we simplify this down, we'll get 0 minus a negative 4, which is going to be a positive 4, all over 5 minus 1, which is a positive 4. So I'll have that f prime of c is going to be equal to 4 over 4, which we can just say that f prime of c is equal to 1. So now we know that the slope of the secant line is equivalent to 1. We're going to find some point along our function within those intervals that has a tangent line slope of 1, essentially a derivative value of 1. And we got to figure out what exactly that derivative is. So scrolling back over, f of x is x squared minus 5x. So if f of x is x squared minus 5x, then f prime of x is going to be 2x minus 5. Taking the derivative of x squared goes to 2x, and then we'll subtract the derivative of 5x, which is 5. So I just need to see when 2x minus 5, if that's my derivative function, when does that equal 1? So I'm going to have 1 equals 2 times my point c minus 5, because remember, I'm solving for that c value. Or you could leave this as x if you felt like it. I'm just going to use the variable c since that's how it fits with the formula. So solving for c, 2 times c minus 5, I'll add 5 to the other side, so 5 equals 2c. And if I divide by 2, that means c is going to equal 5 halves. So 5 halves is the point along my function where the tangent line has a slope of 1, and that matches the slope of the secant line. And you can see that 5 halves is indeed in our interval from 1 to 5. 5 halves is about 2.5, which falls within that interval. Let's move on to our next example, part B. In part B, our function is x cubed minus 2x plus 6 on the interval from 0 to 2. This is indeed differentiable everywhere within our interval, and we have a closed interval, so we can apply the mean value theorem to this. Again, that's the slope of the secant line is equal to the slope of our tangent line, the derivative, at some point within the interval. So if I was to find my g prime of x at the start, that's going to be 3x squared minus the derivative of 2x is 2. So if a is 0 and b is 2, then we're going to do f of b minus f of a all over b minus a. Or in this case, g of b minus g of a all over b minus a. So we're going to do g of 2 minus g of 0, and that's all over 2 minus 0. And that again is equal to the derivative at our point c, so g prime of c. So this slope of the secant line we're going to calculate now by plugging 2 in to get g of 2. So that'll be 2 cubed, which is 8, minus 2 times 2 is 4, plus 6. 8 minus 4 is 4, plus 6. That will be a positive 10. So we're going to get 10 minus, now plugging in 0, 0 cubed minus 2 times 0 plus 6 will leave us with 6, and that's all over 2 minus 0, which is 2. And that's going to be equivalent to g prime of c, which g prime of c is 3 times c, that squared, minus 2. So we have 10 minus 6 over 2, so the slope of our secant line is 4, and we have to figure out when that equals 3c squared minus 2. So now I just have to solve for c. And in order to do that, I'll move this minus 2 to the other side by adding 2 to both sides. So I'm going to get that 6 equals 3c squared. And then divide by 3 to isolate that c, so we're going to get 2 equal to c squared. In order to solve for c, we'll take the square root. So we'll get the square root of 2 equals c, and remember when we take the square root, that gives us a plus or a minus. But our c value we're looking for falls in this interval, so we're not going to have a negative root 2 in that interval, so we know that our c is equal to positive square root of 2. So when our x value is equal to root 2, that derivative at that point is equal to the slope of the secant line of the endpoints of our interval. So let's move on to part C. In part C, we have h of x equals the absolute value of 3x on the interval from -1 to 1. Remember, we need to double check. Do we have that closed interval? Yeah, we have the closed interval from -1 to 1. Are we differentiable everywhere on that interval? No, we are not. Therefore, the mean value theorem does not even apply in part C, because think about what the absolute value of 3x looks like. The absolute value of 3x, we're going to get a corner at the point 0. 0 falls in our interval, and we are not differentiable at that sharp corner. Therefore, the mean value theorem does not apply. So we are unable to find C. Let's move on now to Rolle's theorem. Now Rolle's theorem, I like to think about as more of just like a specific case of the mean value theorem, where the slope of the secant line formed by the endpoints of the interval is equal to 0. So if we know for a fact that those endpoints form a secant line where the slope is 0, then our derivative is 0 somewhere else within that interval. So Rolle's theorem is really just a very specific case of the mean value theorem. So if you remember from up above, mean value theorem was f of b minus f of a all over b minus a. The slope of the secant line from our endpoints a and b is equal to f prime of c. But if that slope of the secant line is equal to 0, well, then we know that 0 is going to be equal to f prime of c. So here is the general mean value theorem, and here is Rolle's theorem, that 0 is going to be equal to f prime of c. Now the conditions to this are fairly similar to the mean value theorem, except we have an extra condition. Not only do we have to be on a closed interval, and also our function is differentiable within that interval, but we also have the fact that f of a needs to equal f of b. Because think about it, if I want my slope to equal 0, I need this numerator to equal 0. And the only way that numerator is ever going to be 0 is if f of b is equal to f of a. So Rolle's theorem, the same conditions as mean value theorem, plus one extra condition. F of a equals f of b. So let's go ahead and look below. For each of the following, we're going to find the point or points C when applying Rolle's theorem. So zooming on in, our first part of example 2 says that f of x is equal to x squared plus 3 on the interval from -1 to 1. Well, first off, do we have a closed interval? Yes. Is our function differentiable on our closed interval? Yeah, x squared plus 3 is actually differentiable everywhere along that function. So because we meet those first two conditions, we also have to check our final condition. Does f of -1 equal f of 1? That is our big question we have to figure out. If that's the case, then we can apply Rolle's theorem and find that point C where the slope of that tangent line is equal to 0, because the slope of the secant line, if these are equal, is 0. So plugging in -1 for x, I'll get -1 squared, which is 1, plus 3, which gives me 4. And then when I plug in 1 squared is 1, plus 3 gives me 4. So yes, f of -1 equals f of 1. So I know that that slope of my secant line is 0. So I need to see, when does 0 equal f prime of c? What point C is the derivative equal to 0? And remember that C that I find is going to fall somewhere within this interval. And I can have multiple C values that fall in that interval, but if C falls outside of that interval, then I cannot use it for my answer. So let's go ahead and find what f prime of c is and when that equals 0. So I'm going to have that 0 is equal to, what's my derivative? F prime of x. F prime of x is going to equal, what's the derivative of x squared? That's 2x plus the derivative of 3. Well, the derivative of 3 is just 0. So f prime of x is 2x, so f prime of c, 2c. When does that equal 0? 2c equals 0 when 0 is equal to c. And 0 does indeed fall in my interval. And if you want to visualize this really quickly, just because sometimes I think it helps to have a visualization to further emphasize the concepts, I'm going to do a quick sketch of the graph. X cubed plus 3 is a parabola that opens up, and it has an intercept, a y-intercept of 3. So if this is 3 in the y here, and our parabola opens up, remember, this even function is symmetrical. So when we're at +1 or -1, we're going to be at the same function value. So if here's -1 and here is +1, you can see that that slope of the secant line is indeed 0. And at the point 0, we also have a tangent line that's horizontal, a derivative of 0. Let's move on to part B. In part B, we say that g of x is equal to sine of x on the interval from 0 to pi. So, three things, right? First, do we have a closed interval? Yes. Second, is our function differentiable in that interval? Yes. And then third, does f of a equal f of b? So, in this case, does g of 0 equal g of pi? That is our question. If I plug 0 in for sine of x, I'll get sine of 0, and if I plug pi in for sine of x, I'll get sine of pi. Does sine of 0 equal sine of pi? Sine of 0 is 0, and sine of pi is 0. 0 does indeed equal 0, so yes, f of a equals f of b. And because they're equivalent, I can use Rolle's theorem. Because the slope of my secant line equals 0, I just need to see what point C has a derivative value of 0. And that C will fall within my interval. So taking the derivative of g of x, g prime of x is equal to derivative of sine of x is cosine of x. So I need to see when does 0 equal the cosine of C. What value C gives me a function value of 0? When does the cosine of C equal 0? Think about that unit circle again. Cosine of C equals 0 at pi over 2, 3 pi over 2, and so on. So we have multiple different potential C values, but remember our interval. Our interval is from 0 to pi, so we're only looking at this upper half of our unit circle and only from 0 to pi. And there's only one point that falls in that, and that's pi over 2. So C is going to be equal to pi over 2. So at pi over 2, our derivative is also 0. Now remember, 3 pi over 2 is also 0, and plus another pi, plus pi, and so on. Because this sine of x is cyclical, and the cosine of x also oscillates, we're going to get multiple potential values, but remember, C has to fall in that interval. So even though I have lots of other C's outside that interval, my answer is only the C that falls within that interval. So now moving on to our last example part on this worksheet, part C says that h of x equals x cubed minus 2x plus 8 on the interval from 1 to 2. All right, remember 3 questions for Rolle's theorem. Do we have a closed interval? Yes. Are we differentiable on that closed interval? Yes. So now my next question is, does h of 1 equal h of 2? Are my function values of my endpoints equivalent? So I'm going to figure out h of 1 and see if that is equal to h of 2. Plugging in 1, I'll get 1 cubed, which is 1, minus 2 times 1, so minus 2, plus 8. 1 minus 2 is a negative 1, plus 8 is going to be a positive 7. And then, does that equal h of 2? Plugging 2 in, 2 cubed is 8. 8 minus 2 times 2 is going to be 8 minus 4, plus 8. 8 minus 4 is 4, plus 8 is going to give me 12. 12 does not equal 7, so what are we going to say? We're going to say that Rolle's theorem does not apply. However, if we were asked to use mean value theorem, we totally could, because remember, for mean value theorem, those function values of our endpoints don't have to be equivalent. But for Rolle's theorem, because our slope of our secant line is 0, that's a very specific value, and that only happens when f of b is equal to f of a. So Rolle's theorem in this case does not apply. And with that, we wrap up this worksheet, the mean value theorem worksheet. If you have any other questions, please feel free to reach out and let me know. And continue on to the next example worksheet, where we'll go over some more Calculus 1 concepts. But until then, good luck with your online learning.